Okay, good morning everyone. Okay, so today we will be discussing, we'll be starting a new module which is the electromagnetics fields. Okay, so till now we have studied about the electrostatic field. Now today we will be starting the new module of electromagnetic field. Now basically electromagnetic field, okay, am I audible? Please confirm.
Yes, sir.
Okay, thank you. So in in magnetostatic field, okay, in magnetostatic field we will only discuss about the concept of the magnetism, okay, the field created by a magnet, because in electrostatics we have discussed about the field created by a electric charge, okay, an electric charge. So if there is an electric charge which will create an electric field, so what are the properties, okay, so what is the orientation of the flux, okay, what are the properties, what are the different equations related to electrostatics that we have seen. Similarly for magnetostatics also we will see the same properties, okay, with respect to magnetism, and then we will be combining them to get the electromagnetic effect, okay. And magnetostatic, since you know that a magnetic field is created by a bar magnet, okay, so or a particular magnetic dipole, because in electric field you can see that electric charge exists as a single, okay, that means a single charge exists, that is you can have a plus q or a minus q. Okay, so a single charge can exist, but in magnetism, a single pole cannot exist. You cannot have only a north pole or a south pole. You have to have two poles at the same time, north pole and south pole. That means if you are taking a bar magnet, you will see that it has two sides, one north pole and south pole. And if you want to create a magnetic field using an electrical solenoid, that means electromagnetism. That means you are applying electric current to produce an magnetic field. Okay, so that means in solenoid we have seen that when we wind some conductor on the particular core material, okay, ferromagnetic core. Okay, so when we pass current I, and suppose the number of windings on the particular core is n, okay, so the mmf, the magnetomotive force, will be n into I, okay. Okay, so that is the driving force, so that will create some magnetic flux, okay, so that current is actually creating the magnetic flux, okay. Magnetic flux is also created by the, not the current, actually the mmf rather, okay, so it is created by the mmf. So because flux is very similar, yeah, there is magnetic flux. Don't get confused with electric flux. Electric flux is different. Electric flux, as we know, that it is represented by, okay, if I show you, uh, it will be easier for you to understand. That these two things are very different, okay. First of all, we start with an electric charge, okay. We have a point charge like this, okay, a point charge q, and it is placed inside a particular, or you can say a particular sphere. So it will create some magnetic flux. Flux will come out of the surface. The total amount of flux coming out will be psi, and is equals to the charge enclosed by the particular surface. Why? As per the Gauss law, okay. And flux, electric flux unit is also coulomb. It is also coulomb, okay. But on the contrary, if you consider a magnetic field is created by a, suppose a bar magnet or a solenoid, whatever. Because if you take a solenoid, if I consider a solenoid, okay, suppose this is an iron core, it is an iron core, okay, and I am using some windings, okay, on the iron core, and giving some, say, voltage or a AC voltage, suppose, or suppose a DC battery, okay, DC battery with it will create a flux or variable resistance like this. this is V, so it is carrying current I, and number of turns is N. So MMF will be magnetic force will be N into I. So then it will have a north pole and south pole. It will create a north pole and south pole. Imaginary north pole and south pole it will create, and it will create some flux. Okay, it will create some flux like this. Flux lines will flow like this. These are the magnetic lines of force. Okay, magnetic lines of force. This N is the number of turns actually, not the north pole south pole. This is the number of turns. Okay, magnetic lines of force starts from north pole and ends at south pole outside, and inside also it flows from south pole to north pole. Okay, it continues like this. We all know. Now what are actually flowing through these flux lines? Because these lines are created by somebody. That are the magnetic flux. Okay, we represented by phi. Okay, these are the magnetic flux, and its unit is Weber. Okay, its unit is Weber. Now magnetic flux which are flowing, it is similar to a current in a conductor, because the magnetic fluxes are flowing depending upon the MMF. So the flux which is created is proportional to the MMF, because MMF divided by the reluctance. Okay, you must have studied in your basic electrical. Okay, reluctance gives you the flux. Okay, it gives you the flux. So these are the magnetic lines of force created by the magnetic flux, which is very different with respect to electric flux. But there is the properties, okay, but they are analogy because they are of two families. But in every family, the relationships will be similar, because there is a relationship with flux. Okay, suppose I want to say that both of them are of different families, but since the relationship of family, suppose you have a brother, sister, mother, father, in every family there is the same relationship. So here also similarly, if I say that the flux density D, electric flux density, which is equals to D by area, phi by area. Similarly here also we have magnetic flux density, which is represented by B, which is phi by A. Okay, this is one relationship. Similar relationship. Okay, another relationship is that over here D is equals to epsilon E. That is, the electric flux density is equals to permittivity multiplied by electric field intensity. In magnetic field, there is another similar relationship where B, because D is analogous to B, equals to mu. Why? Because in magnetic field we have permeability. In electric field we have permittivity. In magnetic field we have permeability. Okay, because every magnetic ferromagnetic core has its own permeability. Okay, so it is equals to H, where H is the magnetic field intensity, where E was electric field intensity, H is the magnetic field intensity. Similar to that. Okay, it is analogous to it. Okay, so this is one relationship. These are the two relationships. Okay, so here also the same thing has been explained over here. So till now we have discussed about the E and D. Okay, now similar to that, D and E, we have also B and H. Okay, so this is a table which shows the relationship between the two, means the relationships, comparison of the relationship between the two electric field and magnetic field, or you can say the analogy between. What is analogy? Analogy means where we have similar kind of relationships, okay, or characteristics of one particular area or one particular element with respect to other, so we can draw an analogy with it. Okay, we can draw an analogy, some like that, because see, suppose we talk about force. Okay, so basic law of force. So in electrostatic we know Coulomb's law of force. Okay, Coulomb's law. In magnetic field also we have similar kind of a force, which is called the dB. Okay, that means the force experienced by a particular, you can say, conductor when placed in a magnetic field. That will be seen later from Bayes-Saul's law. Okay, so when we have a current carrying conductor in a particular magnetic field, the current carrying conductor experiences a force, so it starts to move. Okay, similarly, from we have this particular equation of Gauss law. From here also we can get the same similar kind of equation in from the Biot-Savart's law also. Okay, just as I told you that the analogy between D and B, this is also flux density, but electric flux density, this is magnetic flux density. This is electric flux, this is magnetic flux. This is electric field intensity, this is magnetic field intensity. So these are very much analogous to each other, very similar to each other. Because here also it is doing the whatever per work E is doing in electric field, H is also doing the same thing in the magnetic field. Okay, that is what is called the analogy. Okay, so we will be discussing about all the analogies later on. Okay, now coming to the Biot-Savart's law. Now Biot-Savart's law, since you have already studied in the previous classes, okay, maybe in the BTech, in the HS level also, but still we will be discussing it, because over here we will be discussing with respect to vector as well as with respect to the coordinate system. Okay, so Biot-Savart's law states that the magnetic field intensity, that is the dH produced at a point by the differential current element IDL is proportional to the product IDL and the sine of the angle between them, between the element and the line joining the element, that is inversely proportional to the square of the distance r between the P and the element. Now one thing over here, one analogy is represented over here. If you see, it is not given here. Okay, in magnetic field, okay, in magnetic field we will not discuss or we will not talk about electric charge, obviously, because in electric field we have discussed that electric charge is creating a particular electric charge is creating an electric field. But in magnetism, okay, or you can say magnetic field, we don't have a point pole, okay, or we will also not take a bar magnet. So how we will be defined as a magnetic source? Because in electric field, what we have done, we have taken a charge and we have told that there is a electric field over here, and whatever comes inside this will experience a force, so it is creating some flux. In magnetic studies, okay, in magnetic field, we will not consider any bar magnet. We will consider a small current carrying element. Suppose a conductor, a small conductor whose length is dl and carrying the current I. So that current will create some magnetic field, because we know that current carrying conductors create magnetic field. Okay. Okay, because current carrying conductors create magnetic field. So the current carrying conductor, how? Because from right hand thumb rule we have seen that when a current passes like this, the magnetic field is created circling the conductor in this particular direction. As if you point your thumb towards the direction of the current and the direction in which your fingers gets curled, okay, in that direction the field is rotating. Okay, the field is rotating in this direction. Okay, that is why we will consider a particular current carrying conductor, small current carrying conductor like this, DL, and current is IL. Okay, now what will happen if a current carrying conductor, okay, is flowing? So it will create some magnetic field and it will create a magnetic field intensity DH. So it is creating a magnetic field intensity DH at a particular point. Okay, now DH is actually magnetic field which is rotating, because as I have told you, because this is the magnetic lines of force, magnetic lines of force, this red color, it is circling the conductor. So magnetic lines of force means what is flowing through the magnetic lines of force, what is flowing, fluxes are flowing. So fluxes are flowing through the magnetic lines of force. Okay, Okay, so now when the magnetic lines of force is created by the flux, now similarly in electric field, if you see why I am showing electric field, because so that you can understand, grab it faster. In electric field, what we have seen, that if you have an enclosed surface like this, and if you put a charge inside the in that particular surface, the charge will create emit fluxes. Fluxes will come out of the charge like this. So there is no pattern in magnetic field. We have a pattern. It is circling. In a conductor, it is circling. Another one has entered. In a conductor, the magnetic field lines circle around the conductor, and in a bar magnet, what happens? In a bar magnet, what happens? In a bar magnet, the magnetic field line starts from north pole and ends at south pole. So it is following a pattern. In electric field, there is no pattern. It starts from the point and it ends up anywhere. Okay, it comes out of this charge. Now when it is coming out of the charge, it is creating some electric field. Similarly, magnet also creates some magnetic field. If the current is more, the lines of force will be broader, okay, wider. And the current is less, it will be very narrow towards the conductor. Now in electric field, if the charge is more, the fluxes will be more, because Q is equals to F, so fluxes will be more. So electric field intensity will also be more. Electric field intensity means any point inside the electric field, if you put any charge, okay, it will be either attracted or repelled. That means the force experienced by a unipositive charge when placed at that particular point. Similarly, in magnetic field also, it is creating some magnetic field. So at every point there is some magnetic field intensity. So if you put any other magnet within that periphery, it will be attracted or repelled. So that means there is a magnetic field intensity everywhere. Similarly, here also, if this is a small current carrying conductor, okay, or you can say this is an entire conductor over here. Suppose the entire conductor length is starting from here to here, a long conductor, but we have taken only smaller section of the conductor. Okay, now the current which is flowing is I. Okay, now it will create the magnetic field like this, field lines like this. Okay, it will create the magnetic field lines. Similarly, it is told that the magnetic field lines are huge, so it is flowing like this. Okay, it is flowing like this. That is why we have taken this point P. That means it is reaching up to point P, maximum point P it is reaching. Okay, so magnetic field लाइन जो है वो point P तक है, so इसलिए ऐसा सर्कल मूव कर रहा है. ठीक है, छोटा छोटा सर्कल है लेकिन मैक्सिमम रीच इसका point P तक है. Now you can see over here there is a cross sign. Why cross sign? Because in two dimensional, when you are representing anything on paper or a screen, we represent the movement either by dot sign or cross sign. Dot means it is coming out, cross sign means it is entering the surface. So over here, since the arrow, if you follow the arrow, it is entering the surface, so it will be cross sign over here. And if you draw another point over here, then over there if you take the same distance and if you draw over here DH2, then you will have to give the dot sign because the fluxes are coming out from that particular surface. Okay, it's just the opposite. Okay, so the field intensity is at this point is dH. Okay, so it is told that the magnetic field intensity at the point P is dH. Okay, which is created by the produced at the point by the differential current carrying element IDL. IDL is the differential current carrying element. This term has to be noted down. Means differential current carrying element means a small part. Differential, that is why DL is there, because total L we are not taking, we are taking only DL. So this particular small part is creating some magnetic field intensity of DH. If you take the entire length L, so it will be H. So DH is due to DL, H will be due to total L. So here also the same thing of integration comes. Okay, so since we have taken DL, we will take DH. Okay, DH is the magnetic field intensity at point P by current carrying element IDL. So the current carrying element we call it IDL. So we multiply current with the distance, or length. It is similar to charge. In electric field, we do the equation with respect to charge q. In magnetic field, which is created by some current, we take IDL as the magnetic charge, suppose. Okay. So the DH, which is created by IDL, is proportional to the product IDL and the sine of the angle between the element and the line joining P. That means this length is suppose DL, okay, and suppose this point P is maybe perpendicular, may not be perpendicular, so there can be some angle. It can be like this. Suppose this is the DL length and point P is over here, so the angle is like this. If it is over here, then it is 90 degree, otherwise it can be some any angle alpha. So that means this is the current carrying element DL and this is the point P. So the DL is making an angle alpha with respect to point P. Okay, so it is making some angle alpha with respect to point P. So it is told that the DH, which is created by IDL, this one is proportional to the product of IDL and the sine of the angle between them. Okay, that means IDL into sine alpha. Okay, and is inversely proportional to the square of the distance. If the distance is r, so it is inversely proportional to the square of the distance. So the equation is like this: the DH is proportional to IDL into sine alpha by r square. Okay, so DH is, since proportional, we are lifting the proportionality sign, so we are replacing with a constant. So k IDL sine alpha by r square, where k is the proportionality constant, and in SI unit k is 1 by 4 pi. Generally it is observed that after experiments and calculations, k is 1 by 4 pi. So the equation number 2 becomes, you replace k with 1 by 4 pi, it becomes dH equals to IDL sine alpha by 4 pi r square. This is the equation of D due to the current carrying element IDL. So from definition, it is easy to notice that equation number 3 is better put in vector form, because IDL is a vector. Now this is one major difference with respect to electric field and magnetic field. In electric field, the charge Q was a scalar quantity, it was not a vector. Yes, force created by it is a vector, electric field intensity created by it is a vector, potential is a scalar. Okay, D is flux density is also a vector, flux is a scalar. So overall Q was a scalar. Okay, that we have to keep in mind now, rest we will be seeing later on. So Q was a scalar. In electric field, magnetic field, the magnetic charge, or we can say the source, okay, which is creating the magnetic field, current element, differential current element IDL, it is a vector. It is considered to be a vector. Okay, so IDL is a vector. Now if you multiply, suppose IDL sine alpha, that means sine means what? It is some cross product, because we represent, suppose if you write AB sine theta, which means that A is the modulus or magnitude of vector A, B is the magnitude of vector B. So it is actually a cross product. So cross product is creating this sine theta, where theta is the angle between vector A and vector B. Okay, this is theta. So that means if alpha is there, sine alpha is there, that means the vector IDL, okay, and there is some another vector with respect to which we are doing the cross product. So some vector. But since we don't have any vector, because IDL sine alpha, so IDL sine alpha, so alpha is the angle between them, between the vector and the point. Okay, so in this case what we see, AB sine theta, so A and B we know two vectors are there, but over here we have ideal sine alpha. So ideal is a vector, sine alpha, so alpha is the angle. What about the other vector? So that means there is a unity vector. That is, if you write ideal, and most importantly, with which it is making the angle with respect to the distance. So this distance, length, distance from ideal to point P is r distance. So we know distance is a vector, r is a vector. Okay, so the length will be r. Suppose capital R is the mod value. Okay, and r cap is the, or if I write in this it will be easier, or you will get confused. So capital R means the mod value of the length, suppose in meter, 1 meter, 2 meter, whatever, and r cap means the vector. So that means r cap is equals to mod r into unit vector r. That means the direction which is representing the arrow, it is having some unit vector. So with respect to unit vector, this angle is created, isn't it? Because ideal is having some angle alpha with respect to P, but traveling through whom? Traveling through the length. If the length was not there, how can you trace point P? Then what angle will be there? इस एंगल को रिप्रेजेंट करने के लिए इस लेंथ को तो लेना पड़ेगा ना, तो लेंथ के साथ एंगल है, तो मतलब आइडियल क्रॉस प्रोडक्ट विथ यूनिट वेक्टर gives you ideal sine phi. Now the definition is proper. Now you can, because if I represent in this way, that we have a vector ideal, okay, this length, okay, this small length which is ideal, and there is a point P over here, and it is making some angle alpha with respect to point P, and the length is r, mod value. Okay, and the unit vector is AR, and this is itself a vector. So this is one vector, this is another vector. So both the vectors are making an angle phi with respect to each other, just like this. A and B are making some angle theta with respect to each other. Here also ideal and R are making an angle phi alpha with respect to each other. So it will be ideal cross unit vector. Okay, unit vector R, not the actual vector, unit vector R. Okay, because we have seen that it is unit vector R only, because there is no R term. अगर R ऊपर होता तो हम R लिखते. Okay, so this will be mod value, ideal is mod value into 1 into sine alpha. That is ideal sine alpha. That is why it is ideal unit vector R. Now if I replace unit vector with the actual vector, okay, मान this is the cap 1, okay, actual vector. So actual vector means mod value into unit vector. So unit vector is equals to actual vector by mod value. तो ऊपर अगर एक्चुअल वेक्टर आ गया, नीचे मॉड वैल्यू और आगे जाएगा, तो आर स्क्वायर से आर क्यूब हो जाएगा. सेम थिंग विच वी हैव सीन इन दी कूलम्स लॉ. सिमिलर थिंग वी हैव सीन इन कूलम्स लॉ आल्सो. ओके, दिस इज द यूनिट वेक्टर. Thus the direction of the DH can be determined by the right hand rule, with the right hand thumb pointing in the direction of the current and right fingers encircling the direction of the DH. So I have already told that this is the direction. Okay, so it is entering the screen, that is why it is given in cross, and over here it will be given as a point. अगर यहाँ पर हम रिप्रेजेंट करते हैं, ये यहाँ पर भी तो होगा ना लेंथ, यहाँ पर भी एक है, तो ये तो यहाँ से अगर जा रहा है तो यहाँ से आएगा, यहाँ पर डॉट देते हैं हम लोग, डॉट. ओके, दिस विल बी डॉट. Okay, so this is the direction, and alternatively we can use the right hand screw rule, the same thing. Okay, screw rule will be also be applied. Okay, so this is the diagram to represent that. If this is the current flowing, then the direction of the electric field intensity or flux or lines of force or magnetic lines of force, magnetic field intensity will be circling the conductor in this way, in anti-clockwise direction, if you see from the top. And using of the screw also, we can see the screw is rotating in anticlockwise direction from the top. It can be represented like this. So the magnetic lines of force, actually if you see from the top, it is anticlockwise. Okay. Now same thing. Now this is the case. Okay. So it is a customary to represent the direction of the magnetic field intensity by a small circle dot, as we have already told. Okay, so we represent it like this. The cross means it is going inside, is in, and dot means it is out. Okay, so already told, and it is also shown in this particular PPT slide. Okay, so it will help you. Okay, so till now, do you have any question? Anyone regarding Bar-Sava's law? Have you understood? Any questions from your side?
Sir, what is the syllabus of second internal?
Second internal, I have not told. Okay, so I will be telling you by the next class. Okay, in the next class I will tell you. I have not decided yet. Okay, so I will tell you in the next class. So all of you know the mode of exam, isn't it? Now only MCQ is not there. You have to prepare subjective also. You have to write the questions also, answer also. Okay, you must have gone through the notice. There the instruction is given that you have to, on the exam time, the question will be given to you on the screen. You have to solve the question in a paper. Okay, and you have to upload it, and your exam will be conducted virtually, so you have to keep your camera on, because you have to write the exam. The teachers will be seeing you while you're writing your exam, just like a physical exam, but through virtual mode. So it is kind of a say virtually physical exam. Okay, so you must prepare accordingly. So by the next class I will give you the syllabus, or you can say by tomorrow I will tell you the syllabus. Okay, like tomorrow, day after tomorrow. Okay, so any further questions, so that I can end the class up to here. Okay, so we will continue the discussion regarding this Bar-Sava's law and in magnetic field in the next class. Okay, so I have also uploaded the PPTs, lecture notes. Okay, updated my lectures note rather, I would say, in the Google Classroom yesterday, so you can go through them. Okay, so obviously whatever was there in the first slot, after that there will be in the second slot. Okay, so you must go through them. Okay, so class, so I'm leaving the class up to here, and so you can leave. Okay, thank you.